Hello, Algebra 1. This video is our first video key for one of our homework assignments, and we're going to start with 7.5. That was the difference of squares. So the point of these video keys are going to be going to work through all the problems on the homework for you. So you can use those if you're stuck or if you're having some trouble figuring out a step. Hopefully this will get you past that, get you unstuck and onto the right answer. So let's get started with number 1. Okay, here's number 1, n squared minus 64. Now up in the corner here, I wrote our difference of squares formula. So we're looking for a squared minus b squared. Basically, we're looking for a perfect square minus a perfect square, and that's going to equal a plus b times a minus b. So look at our problem here. Do we have a perfect square here in n squared? Yes, we do, because that is n times n. So do we have a perfect square here in 64? Yes, we do. It is 8 times 8. So we could actually rewrite that. Well, this would still be n squared, and this would be 8 squared. So you can see how this looks a lot like a squared minus b squared, except this is n squared minus 8 squared. So if we were to substitute this in, basically our a would be n, and for a formula, our b would be 8. So hopefully you can see that it's a perfect square minus a perfect square. A squared minus b squared, we have n squared minus 8 squared. And we plug that into our formula, we're going to end up with n plus 8 times n minus 8. So in solving all these problems, the two things we're going to need to do, first identify if we have a perfect square minus a perfect square. We did here. And then we have to identify what our a is and what our b is. Okay, in this case our a is n because it's m times n. And our b is 8 because it's 8 times 8. So our answer is n plus 8 times n minus 8 for number 1. And let's move on to number 2. Okay, so here's number 2, c squared minus 100. So we have to, again, look at each term here and see, do I have perfect squares? Do I have a perfect square in c squared? Sure. That's c times c. Do I have a perfect square in 100? I sure do. That's 10 times 10. So we can rewrite this as c squared minus 10 squared. And you can see how we have perfect square minus perfect square. So it matches our a squared minus b squared formula. So we're going to end up with c plus 10, c minus 10. And there's our answer for number 2. Now on to number 3. Okay, here's number 3, 9b squared minus 100. So again, we look at each term. Do we have a perfect square? Is 9b squared a perfect square? Actually, yes, it is. We can look at each part individually. So is 9 a perfect square? Sure. 3 times 3. Is b a perfect square? Yeah. b times b. So if we take that term in its entirety, 3b times 3b equals 9b squared. Now let's just look at 100. Is that a perfect square? Yes, it is. That is 10 times 10. So if we wanted to rewrite this, we could rewrite it as 3b squared minus 10 squared. So now we have a perfect square minus a perfect square. We match our rule up there again. So our answer would be 3b plus 10, 3b minus 10. Okay, and that would be our answer for number 3. So let's take a look at number 4. Okay, here's number 4, 25x squared minus 49. So again, in our first term, do we have a perfect square? Yes, we do. Look at each part individually. The number first, 25, that's 5 times 5. X squared is x times x. So we do have a perfect square there, and it is 5x times 5x. Multiplying those two together does give us 25x squared. How about 49? Do we have a perfect square? Sure do. That's 7 times 7. So if we were to rewrite this, we would have 5x squared minus 7 squared. So we have perfect square minus a perfect square. We match our rule. And so we factor this, it would be 5x plus 7, 5x minus 7. And there is our answer for number 4. Take a look at number 5. Okay, so here's number 5, 16a squared minus 121. Let's look at each individual term. 16a squared, is that a perfect square? Yes, it is, because 4 times 4 is 16, a times a is a squared. So this is actually 4a times 4a. Multiplying 4a times 4a, we get 16a squared. How about 121? Is that a perfect square? It is. It's 11 times 11. So we can rewrite this as 4a squared minus 11 squared. You see we have perfect square minus perfect square, so we fit our rule. And our answer will be 4a plus 11, 4a minus 11. Sorry, it's a bad looking A there. 4a plus 11, 4a minus 11. And there is your answer for number 5. Okay, so here's number 6. It is 2n squared minus 72. And questions 6 through 10 are interesting because we're going to have to use a combination of greatest common factor, which we learned earlier, along with the difference of squares. So let's start by looking at each individual part here. Is 2n squared a perfect square? You might think so because it has that n squared there, and it's n times n. But 2 is not a perfect square. So this term is not a perfect square. Both of these parts have to be perfect squares in order for the whole term to be a perfect square. And because that 2 is not a perfect square, this first term is not a perfect square. How about 72? Is 72 a perfect square? It is not. There's nothing I can multiply by itself to get 72. So now we have to look for a greatest common factor. Well, what's the greatest common factor between 2n squared and 72? We only have an n here, no n there. But we do have numbers on both, so we have to look at the factors of 2 and the factors of 72. Our greatest common factor is going to be 2. So once we factor a 2 out of this expression up here, factor the 2 out, that'll leave us with n squared minus 36. Now that we've factored out that common factor, we look at what's left inside the parentheses. Do we have a perfect square here? Yes, we do, because this here is n times n, and this 36 here is 6 times 6. So we have a perfect square. So we could rewrite that as 2 times n squared minus 6 squared. See, perfect square minus perfect square, so we fit our rule. So we can't forget to keep carrying our 2 down. But when we separate this into our factor, we're going to get n plus 6, n minus 6. And that is our answer for number 6. Okay. So the only difference in how we solve this one when compared to the first 5 is that we had to find that greatest common factor and factor that out first. Okay, let's take a look at number 7. Okay, here's number 7, 18x squared minus 50. Do we have perfect squares here? We do not, because 18 is not a perfect square, nor is 50 a perfect square. So we have to look for a greatest common factor to come out of both of those. So if we don't see it right away, we can list our factors. So if we look at 18, our factors are 1, 2, 3, 6, 9, and 18. Those are our factors of 18. If we take a look at our factors of 50, we'll have 1, 2, 5, 10, 25, and 50. So those are all the factors of 18 here and 50 here. Okay. If you're a little rusty on that, this was the first unit we did, first lesson we did in this factoring unit way back right after spring break. Okay. So when we're looking for the greatest common factor, we look at the largest number to appear on both lists. We have 2 will be our largest one, will be our greatest common factor. So we're going to pull a 2 out of this expression here. We can erase this list now that we're done. And we'll be left with 9x squared minus 25 when we pull that 2 out. So now let's look, do we have perfect squares? Well, is 9 a perfect square? Yep. 3 times 3. X squared a perfect square? Yep. X times x. So we can rewrite 9x squared as 3x times 3x. How about 25? Yes, that's 5 times 5. So rewriting, we have 3x squared minus 5 squared inside our parentheses here. See, we have perfect square minus perfect square, so we can use our rule up here, and we will have 2 times 3x plus 5, 3x minus 5. And there is our answer for number 7. Let's take a look at number 8. Okay, so here is number 8, and we look at each part here, looking for perfect squares. Is 45 a perfect square? It is not. How about 20? It's not either. How about y cubed? No, we need an even exponent for it to be a perfect square. If it's an odd exponent, we don't have a perfect square. How about y? Well, that's y raised to the first power. That's an odd exponent as well. So that's not a perfect square. So we don't have a perfect square in the bunch. So let's look at our numbers first. We got to find greatest common factor. So we'll have 1, 3, 5. Let's see. So 9, 15, 45. Don't think I missed any there. Okay. How about on 20? We have 1, 2, 4, 5, 10, and 20. Okay, so what's our greatest common factor on our list here? It looks like we're going to have 5 and 5. So we're going to pull our 5 out. But how do we treat these odd exponent variables? Let me erase the list here. The easiest way to do it is just look at each one. I have y to the third and I have y to the first. Pull out the one with the smallest exponent. That would be y to the first. Okay? That's always going to be your greatest common factor when you have variables with odd exponents. It's going to be the one with the smallest exponent. So now let's divide 5 into 45. That's 9. We take a y out of y cubed. That leaves us with y squared. If I take a 5 out of 20, it's going to leave us with 4. Of course, y divided by y, well, that's just going to be 1. So that cancels out. So now we look at our two terms here. I have a perfect square here. Yeah, with 9, I got 3 times 3, y squared, y times y. And here's 4, that's also a perfect square of 2 times 2. So this becomes 3y times 3y. That is 2 times 2, or we could rewrite it as 3y squared minus 2 squared. You can see we have a perfect square minus a perfect square. That fits into our rule. So our factor will be 3y plus 2, 3y minus 2. And there's our answer for number 8. Okay, let's take a look at number 9. Okay, here's number 9, 100x cubed minus 36x. Do we have perfect squares? We're okay with 136, but because we have odd number exponents on our variable, that throws out the perfect square possibility. So we're going to have to go greatest common factor. So let's start by looking at the numbers. Let's look at the factors for 100. We'll have 1, 2, 4, 5, looks like 10, and head back down 20, 25, 50, and then finally 100. So there are our factors of 100. Let's look at our factors of 36. We'll have 1, 2, 3, 4, 6. 6 times 6, we start heading back down. We got 9, we'll have 12, 18, and 36. So what is our largest number that shows up on both lists? That would be 4. So we know we're going to be pulling a 4 out of there. Erase our list here. And now we have x cubed and x. We're going to pull out the variable with the smallest exponent. We have to the third here, to the first here. So we're going to pull out the 1 to the first. So what does that leave us? Well, 4 into 100 is 25. X into x cubed is x squared. 4 into 36 is 9. And x divided by x, well, that's 1. That's just going to cancel out there. So now we're left with this inside our parentheses, 25x squared minus 9. Do we have perfect squares? 25 we do, because that's 5 times 5. X squared we do, x times x. So that we can rewrite as 5x times 5x. How about 9? That's 3 times 3. So if we rewrite what we got going on in the parentheses, we'll have 5x squared minus 3 squared. So you see we got perfect square minus perfect square. Falls into our rule. We can rewrite that as 5x plus 3, 5x minus 3. There's our answer for number 9. Okay. Well, let's take a look at our last problem, number 10. Here's our last problem, number 10. 16k to the 5th minus 100k. Do we have perfect squares here? Well, we're okay on our numbers, but you can see we got odd number exponents on our variable again, so we're going to have to look for greatest common factor. Let's look at 16 here. We'll have 1, 2, 4, 8, and 16. 100 will have 1, 2, 4, 5. We have 10, 20, 25, 50, and 100. Okay. What's the largest factor that shows up on both lists? Looks like we're going to have 4. So we know we're going to be pulling a 4 out of there. And let's look at our variable terms here. We take out the one with the smallest exponent. So we have 5 here, 1 here. We're going to pull out k to the first. And when we factor that out, 4 out of 16 leaves us with 4. And k out of k to the fifth leaves us with k to the fourth. We're going to pull 4 out of 100. That leaves us with 25. And k out of k, well, that just cancel each other out there. So now let's look at what we got going on inside the parentheses here. We have perfect squares. 4 is a perfect square, k to the fourth is a perfect square, 25 is a perfect square, so we're in good shape. We can rewrite 2k to the fourth as 2k to the second times 2k to the second, and 25 we can rewrite as 5 times 5. So we can put that as 2k squared squared minus 5 squared. So we have a perfect square here minus a perfect square here. That fits into our rule. So let's rewrite that. The factored form is 2k squared plus 5 times 2k squared minus 5. And there's our answer for number 10. So that's all, a look at all 10 problems on that homework assignment for that particular lesson. If you still have some questions, email me. Otherwise, I hope this helped.